Jai Hind to all. My name is Dhanshri Parihar, Assistant Professor, Department of Computer Science and Engineering. And my today's topic is processor organization from the subject Computer Organization and Architecture. So the contents of my slide include Introduction to Processor Organization, Journal Register Organization Scheme, Single Accumulator Based Organization Scheme, and Stack Organization Scheme. So what is processor organization schemes? So we divide processor organization schemes into three parts. The first one is single register organization scheme, which is accumulator based organization scheme. In this scheme, a single accumulator is used as a general purpose register. And the example of this organization scheme is the basic computer system. The second organization scheme is Journal Register Organization Scheme. This organization scheme includes various general purpose register. They will be acting like a source register as well as your destination registers. And the example of such organization scheme is the modern computers. Now these days we use journal register organization schemes, and it is actually used for 3 address instruction set and 2 address instruction sets. The third organization scheme is stack organization scheme. In a stack organization scheme, all the operations are done by the means of stack on registers as well as on your memory. So let's discuss the very first scheme, that is the journal register organization scheme. In journal register organization scheme, we'd have multiple registers which will be acting as a source register as well as the destination register for transmitting the data from the source to destination register. And this scheme is a very good scheme instead of transferring the data from memory and to the memory. So the reading writing operation in the register is very easy as compared to the memory because of its small size. Now let us have a look at the architecture of journal register organization scheme. As we can say here that we are having 7 journal purpose registers which will be acting as the source as well as the destination registers. We are having 2 multiplexer over here of 8:1. That is 8 into 1 means each multiplexer is having 8 inputs and having 1 output with 3 selection lines. Why only 3 selection lines? As we know that in multiplexer we are having 2 raised power n inputs and n outputs. Sorry, 1 output. So we are having 2 raised power n input means here the value of n is equals to 3. So 2 raised power 8 is equals to, 2 raised power 3 is equals to 8. So we are having 8 inputs and only 1 output, where your input number 1 is coming from the external source. So the input number 1, that is input at 0, is coming from some external source. That will be from the CPU itself. And this is coming from R1, this is coming from R2, R3, R4, R5, R6 and R7. So we are having in total 8 inputs. Similarly, in multiplexer B also, we are having 8 inputs, one coming from the external source, that is the 0 input, and other are coming from one register R1, R2, R3, R4, R5, R6 and R7. And these particular input is selected on the basis of the code of these selection line, that is selection line A and selection line B. selection line A is working for multiplexer A, that is Mercs A, we can say, and the selection line B is working for multiplexer B. So how these are working? There will be the code for the corresponding input. Suppose we are having here R1 need to be selected. What will be the code on this selection line? This will be your 001, like this, 001. That is for selection of register R1 from here and giving it as a output. So R1 is selected from here. So next we are having an ALU, that is your arithmetic and logical unit. Now what is arithmetic and logical unit? Where we perform your arithmetic operation like addition, subtraction, multiplication, division and many other arithmetic operations. For selecting the particular arithmetic operation, we are having the OPR code, that is the OPR code bit, that is the operational code bits. Now what are these bits? These bits will define which kind of operation is performed in your ALU, either addition, either multiplication or arithmetic operation. And we get the output accordingly. Now that output is loaded again to your the destination register. Now how this destination register is selected? That will be selected on the basis of this decoder. So here we are having 3 into 8 line decoder. Hence we are having a 3 selection lines which is known as selection D lines for selecting any one of the register among your 7 registers. So again we are having here the 3 bit of code for making some selection. For example, I want to select R3. So I will be having a code of 011 and this 011 will going to select your R3 register and its corresponding load lines will be getting activated and the value of this load line will become 1 for R3 and 00 for other registers. So at this moment this R3 is only capable of getting the for obtaining your output and all the other registers are non-functional at that particular duration of time. Now let's understand this example, this organization scheme with the help of an example. So here let us assume that we have to perform an operation of addition, adding the contents of register R2 and R3 and the result must be stored in your register R1. So how this operation will be performed in this journal register organization scheme? First we will have a look at the control word. Now what is a control word? It is a set of bits, a signal which is issued by your microprocessor and it will be of 14 bits. Now how it is composed? It will be consisting of 3 bit of selection line of multiplexer A, 3 bit selection line of multiplexer B, 3 bit selection lines of multiplexer D and the 5 bit operation code of arithmetic and logical unit. So in total we are having 14 bit of control word. Now when this control word is issued by a microprocessor, the particular operation is performed accordingly. Now in this example, as we are having 2 register R3 and R2 and we have to perform the addition operation for this particular register and we have to store the result in register R1. So our source register are register R1 and R3 and our destination register is R1. So let us take a look at this truth table where we have certain binary codes according to these selection lines. So what will be the code for register R3, as we need a binary code for R2. So R2 is getting uploaded where that code will be getting uploaded at multiplexer A. Here selection B line is for R3 and selection D line is for R1, that is for destination, and operation code is for addition. Now what will be the code for this R2? By looking at this truth table, the code for R2 is, for selection line A, it is 010, and the code for R3 is 011. So by putting this code in this particular selection format, in the previous diagram, here we are having a code for R2 over here, that is 001. For here we will be having a code for R3, that is 011, and for arithmetic logic unit we are having a code of 5-bit for performing your addition operation between R2 and R3, and that code will be like this. So we are having 11 arithmetic and logical operation, and this is the table which will be showing the corresponding 5-bit code for performing that particular operation. Now, like for transferring the data from to your register A or to operand A, we will be having a code of 000. For incrementing A, we are having 5 4 zeros and 1 1. For addition operation, we have 00010. For subtraction, we have 00101. Decrement operation 00110, and A and ending B. For AND operation, we are having 01000, and for OR operation, we are having 01010. Similarly, for XOR operation, this is the code of 5-bit 01100, complementing 01110, shifting the contents of register A, that is for operand A, that will be 1 4 times 0, and shifting left operation for operand A, we are having 11100. So right now in this example, we are performing an addition operation, and for performing addition operation, what will be the operation code? That operation code is this 00010. So we will be putting this code over here, that is 00010. So we will be putting this code over here, and what we will be performing? We will be performing the addition of R2 and R3, and what will be the result? The addition of R2 and R3, and result will be stored in your R1. So this is your R1 register over here. Now how this result is, the addition result will be stored in the R1 register. For doing this, what we have to do, we have to put the code of that R1 over here, that is decoder will be accepting that code of 3-bit, that will be selection D lines, and the corresponding R1 register will be selected as your destination register by turning on this load line to be 1 for register R1, and hence we will get that addition operation result stored in your register R1. So this will be the operation of this journal register organization scheme, and we can use this journal register organization scheme for 8 registers, for 16 registers, for 32-bit as well as for 64 registers also, but that will increase the complexity of the circuit. So this is the most convenient example for journal register organization, as we are having only 7 register organization, special purpose register over here, or journal purpose register over here. So the next scheme is our stack organization scheme. So the journal register organization scheme is used for 3 address and 2 address instruction, and performing an operation or organizing your 1 address instruction, we will use your stack organization scheme. In a stack organization scheme, we are having further 2 organization scheme. One is your register stack organization scheme, and other is your memory stack organization scheme. Now in these schemes, we will be using the stack LIFO format, that is last in first out format, for pushing and popping the contents from the memory as well as from the register. Now what is a push operation? Push operation is an insertion operation into a memory, and what is a pop operation? Pop operation is the deletion operation from the memory content or from the register. So we will be organizing your register in a form of a stack, or your memory in a form of a stack. So let us consider an example where we are having a memory stack organization scheme, and what we are considering, we are having the addresses in a form of a in a decreasing order, that is from 4001 to 1000. Here in this example, we are considering a RAM memory, and in RAM memory, the location from 4001, that is from location 4001, the address that will be acting like a stack to 3000 location, and the address content from 3000 to 1000 will be acting like acting as a normal memory where we are storing a data, that is the operands as well as your program instructions. Here we are having certain special purpose register like program counter, which will be storing the address of the next instruction to be executed, and next your address register which will be pointing to some address of the memory content, and a stack pointer. Now what is a stack pointer? It is a pointer that will be containing an address of what? The address of the topmost location of your stack. So here we can say that the topmost location is at address 3000. So currently stack pointer is having your location 3000, that is the top of the stack. So insertion and deletion in this stack will be taking in a form of last in first out. So data which will lastly inputted to this particular stack will be first to be getting out of this particular stack. Now let us have a look at this particular operation, how this operation is performed in your memory stack. Like for pushing operation, as we are having these addresses in a decrementing order. So in order to push means in order to insert an element over here, suppose I want to insert an element A over this 4000 location. So what I have to do, I have to decrement. Suppose this stack pointer is currently pointing to this location. So the content of stack pointer is here is this stack pointer contain 4001. It will be containing 4001 right now, the top of the stack. So we are considering that this stack is totally empty and we are not having any operands in this particular stack, and I want to insert this A from outside, that is from data register. We can say this is A, it will be stored in your data register, DR register, and I want to put this A at location 4000. So how I can perform that operation? I can first point out the location where a stack pointer is pointing, that is at 4001 location, and for pushing an operation means to insert that element into stack, we have to decrement the stack. Now why to decrement? Because the addresses are in decreasing order. So if I want to insert element at 4000, so 400 minus 1 will become 4000. So here if stack pointer is currently pointing to 4001, what will be the push operation will become like this, 4001 minus 1, that will be your 4000. So SP will be now pointing to your 4000 location. Now after moving this pointer to this location, now we can perform your insert operation. And what is the statement for performing that insert operation? For performing insert operation, we have this. We have to transfer the content of data register to your memory of stack pointer, that is the address of that memory where the stack pointer is, your stack pointer is pointing, that will be at location 4000, and this is getting inserted into that stack. Now this is the push operation. Now what about the pop operation? That is totally opposite of our push operation, as we have to first, now if I want to delete this A from this stack, what I can do? Now I have A at this particular location and I want to remove this A from this stack. How that can be removed? Now before removing this from the stack, first I have to copy this A to data register. Here we are having a data register that will be of 16-bit. First I have to copy this A to data register, and for performing this that operation we are having this instruction that the memory content where the stack pointer is pointing, that is the address of stack pointer, that is currently it is at 4000. So at 4000 location it is currently pointing, where A, what is that is the location of your element A, and we have to transfer that content to DR. So first we will copy this A to DR, and then I have to decrement this pointer to location 4001. For decrementing operation, as we are performing SP plus 1. Why SP plus 1 again? Because the addresses are in decreasing order. So when we add 1 to this 4000, what we will get? 4001. So here, if it will be 4000, I will be adding 4000 plus 1. It will become equals to your 4001. So this stack pointer is now pointing to this. A will be removed now, and this stack pointer will be now pointing to this location, and your A is removed from location 4000 and will be stored in your data register. So this is how we can organize your memory in a form of a stack. Now another way of organizing your memory, that is your register, again the stack organization scheme, but the difference is in that scheme we are using register for storing the data. In memory organization scheme we are using memory, that is your RAM memory, for storing your data. So next we will move to the register stack organization scheme, which is a bit different from your memory organization scheme. Now in register stack organization scheme, again we are having certain addresses labeled with your stack, and this is your some register, a 63-bit or we can say 64-bit register, and here we are having addresses from 0 to 63, and we have to insert content A, B, C into your stack, or we have to remove this content A, B and C from the stack. Again we are having a stack pointer which is pointing to the top of the stack. I can say top of the stack. So here the top of the stack where the data is available is your location number 3, and it will be of 16-bit. We are assuming it to be of 16-bit here for this particular example. And here you can see we are having two flags also, one named as full and one named as empty. So these flags will be holding only 1 bit of value, that may be either 0 or either 1. So 0 will be indicating that full is not activated, means your stack is not full if it is 0. And the value of if full is equals to 1, it means that your stack is completely filled, means the 64 location of stacks is completely filled. Similar with the case of an empty, if the value of empty is 0, it means your stack is not empty, it will be having some values in it. And if the value of empty is 1, it means there will be nothing in your stack and you cannot perform any deletion operation on it, because we are not having any data inside the stack. So what you will delete if you are not having any data inside your stack or inside your register? So let us take an example to understand the concept of this register stack organization scheme using your stack organization. So again we are having push and pop operations, which is quite different from your memory organization scheme, as we are having two condition over here also, and we have to perform the check for this condition also, and we have to come back to the execution of these instructions. Now initially we will be supposing that your stack pointer is 0, means it will be pointing to your 0 location, this location, and the value of empty is 1, means our stack is not having any value. Like this we can assume it that stack pointer is pointing to this location, and we are having a data register over here from where the content is being transferred to your stack, and this is your 0 location. Then we have 1, 2, 3 and 4. Initially it is empty and we have no content in it. So if it is empty and the stack pointer, that the value of, if it is empty, the value of empty is 1. And if it is not empty, means if it is full like this A, B, C, and it exceeds your 63 value, we have some PQR value, then the value of full will become 1 and the empty will become 0 in that case. But right now the case we are considering it to be an empty stack, not containing any data inside 8. Now let us perform a push operation, insertion operation on this empty stack. So the very first instruction of this push operation is the incrementation of stack pointer. Okay, right now your stack pointer is at 0 location, and by incrementing this, it will be pointing to your location number 1. How? Because the value of stack pointer is 0 and 0 plus 1 is 1. So it will be pointing to location number 1. So stack pointer is currently now become 1. Okay. It will point to location number 1, and now we can perform an insertion operation, means the push operations. And that data is being in your data register. That will, let us assume that data register will be containing your operand A over here, operand A, and this A is now being transferred to your location number 1. This is your A. Now, after transmission of data, we have to check one condition also. What this condition says that if the stack pointer is 0, means it is at 0 location, and then the full is equals to 1. Maybe your full may be equals to 1 and empty will be 0. If this condition is true, then the push operation will not work. If this condition is false, then we have to come back to this increment operation, and again we can insert the elements into your stack. Similarly, we have a pop operation. In popping, we have to remove these elements from your stack. So let us consider again this example for popping operation. In popping, before performing your deletion, what we have to do, we have to transfer those content which we are going to delete from the stack into your data register. So where is the stack pointer is currently pointing? Let us assume that we have to delete this C from your stack. This C we have to delete. This C we have to delete. Okay. So what will be the location of stack pointer? The stack pointer will be pointing at location number 4. And what we have to do before decrementing this stack pointer, we have to transfer this C to a data register. So performing that operation, we have an instruction. The memory content of that stack pointer must be transferred to data register. So this A will be transferred over here, and sorry, that C. And now we are not having this C in your register, and after copying it, we can move this stack pointer to location number 2. So here we are having this operation like this. SP will become, stack pointer is at currently 3, so 3 minus 1 will become 2. Now the stack pointer will be pointing to location number 2, that is to operand B. It will be removed from your stack. This is the way how we can perform a pop operation, and after performing that pop operation, we have to check the condition also. There is one condition, that if stack is 0 and the empty is 1, means if your their stack is not containing any element, delete an element if your stack is empty. So it is an underflow condition of a stack. So we have to check this condition after every deletion operation, and if it is true, no further deletion can be possible. And if it is false, we can come back to this location and again we perform deletion operation. Delete B as well as A, and after A we have nothing to delete in your stack, so this condition will become true and we cannot execute further these two instructions. So this is all about your register stack organization scheme. So the last scheme of processor organization is single accumulator based CPU organization scheme. In this scheme, the CPU organization, the first ALU operand is always stored into an accumulator. Now what is an accumulator? It is a special purpose register, we can say, which can hold 16 bit of data in it, and it can store intermediate results in it. So it can hold only one operand. And what about the second operand? That second operand is present in some other register or in the memory itself. So One address instruction is the example of this organization scheme, and we have certain instructions like load X, store X. Over here it is written over here, load X and store Y. So loading the content of, it means that we can copy the content of operand X into your accumulator AC. Similarly, we can read, we can say, and this is the writing operation. Here load is for reading operation, read the content of operand X, and reading can be performed with your accumulator and store them in your AC, the readed content. Here we can perform a write operation, write the contents from Y to and then store in your accumulator, operand Y to AC. So such kind of instructions are known as your zero address instructions, and for performing these zero instruction, the hardware organization scheme which is used is your single accumulator based organization scheme. So here what we are having, we have a one memory unit, we can say, and we can have an IR register, then we have your accumulator, we have your program counter, and we have a common bus in between them. Here your instruction register is being loaded by this, your accumulator is connecting with this, your program counter is also connected with this, like this. This is your common bus. Okay, and this is connected with all the devices. So what will happen in this organization scheme? The memory will fetch the instruction into your IR register, which is a 16-bit register. And after fetching that instruction, we will come to know that whether that instruction is your 0 address or 1 address or 3 address instruction. If it is a 0 address instruction, it will be having one operand in your accumulator and one operand in your memory unit.